Power System course. It is core course, particularly for third year electrical engineering students. Power system is basically man-made largest dynamic system on the earth. Now we'll start structure of power system. The first one, generating station, transmission lines and the distribution system are the main components of an electric power system. And the second one, the generating station and distribution system are connected through transmission lines, which also connect one power system to another. And the third one, a distribution system connects all the loads in a particular area to the transmission lines. If we look into the schematic diagram of power system, the first one is the generating station. Then you have the step-up transformer. Then transmission system is coming. After that, the tie line to other system. Tie line means three-phase transmission line. It will be further step down. Then you have sub-transmission level of sub-transmission system. And the voltage level is 33 kV to 132 kV. After that, these are the large consumers. And in this side, this is the generating units and this is the step-up transformer. And voltage will be step up to either 33 kV or 132 kV. It will be further step down, then the primary distribution come. Here also the medium large consumers who need power at the voltage level 33 kV or 11 kV. Then secondary distribution system supply power to the domestic or industrial and commercial consumers. In this case, if it is line to line, then 415 volt. And if it is a single phase, then line to neutral 240 volt. That means 415 by root 3. This is the structure of power system. The main components of an overhead line are conductors, support structures and insulators. The conductors are always bare and the vital links in the transmission and distribution system. Generally, ACSR conductors are used. And the support structure, that means poles and towers, are required to serve the purpose of keeping the conductor at a safe height from ground as well as at an adequate distance from each other. And third one, the insulators. Insulate the conductor from ground. Normally two types of insulators. First one, the suspension type, and the second one is the pin type. Now the construction of overhead line involves first one, the choice of support structure, and the number two, pulling and stringing the conductors in such a way that the tension in a conductor does not exceed the permissible limit under worst weather condition. And the number third, the design of insulator structures so that the normal system voltage or abnormal over voltage do not cause breakdown of insulation, resulting in a short circuit of the line conductor with supporting structure. So moreover, the operation of the line should be safe for human beings and environment. Now the topic is conductor material. Aluminium with steel core, that means ACSR. Aluminium conductor, steel reinforced, is widely used for high voltage lines. Other materials used are like cadmium, copper, phosphorus, bronze and galvanized steel. The choice in a particular case depends upon the cost and the required electrical and mechanical properties. Now in this figure, a steel cored aluminium conductor having one steel wire surrounded by 6 wires of aluminium. Steel cored aluminium conductor consists of central core of galvanized steel wires surrounded by a number of aluminium strands. Usually, diameter of both steel and aluminium wires is the same. The cross section of the two metals are generally in the ratio of 1:6, but can be modified to 1:4 in order to get more tensile strength for the conductor. Now, the result of this composite conductor is that the steel core takes greater percentage of mechanical strength, while aluminium strands carrying the bulk of current. Support structure, that means poles or towers, are required to serve the purpose of keeping the conductors at a safe height from ground as well as at an adequate distance from each other. Now the construction of the support depends on the cost. Self-supporting towers made of galvanized steel are generally used for support of high voltage conductors. And for low voltage, steel, concrete or wooden poles may be used. Now the various types of supports. The number 1, wooden poles, and number 2, reinforced concrete poles or RCC poles, and number 3, tubular steel poles, and number 4, lattice steel towers. Wooden poles are the simplest and perhaps the cheapest, but are useful for voltage up to 132 kV. The main advantage of reinforced concrete poles or RCC poles are a very long life and low maintenance charge. They are used up to 33 kV system. Now the tubular steel poles. These are often used as a substitute for wooden poles. They are costlier than wooden or RCC poles, but some advantages are lightweight, long life and higher strength. They are widely used for system up to 33 kV. Now the steel towers are extremely useful for system voltage often above 33 kV with long distance transmission lines. Even though they are 2 or 4 times costlier than wooden poles, yet for tall supports and long spans they prove economical. Mechanical design of overhead lines. Conductor materials. Line supports. Wooden poles. Now reinforced concrete poles. Then tubular steel poles. Then steel towers. And the next, cross arm. Now the topic is sag and clearance. Then what is a cross arm? Cross arm connected to tower or pole support the conductor through insulators. Now what happened? A uniformly loaded inelastic wire stretched between two supports dips or sags from the horizontal plane due to its own weight and hangs in a form of a catenary. Then what is a sag? Sag is defined as a vertical distance between the point where the line is joined to the tower or pole and the lowest point on the line. Now come to the span. The horizontal distance between the adjacent tower is called span, and the vertical distance between the ground and the lowest point on the line is called clearance from ground. The more the sag of the conductor and the lesser the clearance from ground, and vice versa. Now, it is necessary to maintain a certain minimum clearance above ground for safety of human beings. And this is the figure of sag and clearance from ground. Sag and clearance. Now the topic is sag tension relation. The first condition, when supports are at equal levels. That means A and B are at equal levels. Now consider a point P on the conductor, taking the lowest point O as the origin. Let the coordinate of point P be x and y. Assuming that the curvature is so small that curve length is equal to its horizontal projection, that is OP equal to x. Now the two forces acting on the portion OP of the conductor are, number 1, the weight WAX of conductor acting at a distance x2 from O, and the second one, the tension T acting at O. So you can write the first one, the weight Wax of conductor acting at a distance x2 from O. And the second one, the tension T acting at O. Now equating the moments of above two forces about point O, we get, so you can write Ty is equal to Wx into x by 2. So you can write y equal to Wx square by 2t. Now the maximum dip, or we can say the sag, is represented by the value of y at either of the supports A and B. So you can write at support A, x equal to, say x equal to L by 2 and y equal to S. So x equal to L by 2 and y equal to S. So sag S equal to Wx square by 2t. So W L by 2 whole square by 2t, or S equal to WL square by 8t. Second one is when supports are at unequal levels. This figure shows a conductor suspended between two supports A and B which are at different levels. The lowest point on the conductor is O. Now let small l is equal to span length and small h is the difference in levels between two supports. That means h2 minus h1 equal to h. And x1 is equal to x1, the distance of support at lower level, that is A from O, and x2, the distance of support at higher level, that is B from O, and capital T equal to tension in the conductor. And now if the W is the weight per unit length of the conductor, then we can say the sag is 1 to W x1 square by 2t, and sag h2 equal to W x2 square by 2t. Now h2 minus h1 is equal to W by 2t x2 square minus x1 square. And also I can write x1 plus x2 equal to small l. From the figure, x2 plus x1 equal to L. So you can write W by 2t x2 plus x1 x2 minus x1. Also h2 minus s1, we can write h2 minus s1 equal to h. So h equal to W by 2t x2 plus x1 to x2 minus x1. Now put the value x2 plus x1 L x2 minus x1, or x2 minus x1 equal to, we can write 2th by WL, equation 2. Now solve equation 1 and 2. We get x1 is equal to L by 2 minus th by WL, and x2 equal to L by 2 plus th by WL. From here, the values of S1 and S2 can be easily calculated. Sag and tension relation. Now I will put a question here. The towers of height say 40 meter and 80 meter respectively support a transmission line conductor at water crossing. Now the horizontal distance between the towers is 600 meter. If the tension in the conductor is 1800 kg, then find the minimum clearance of the conductor and water and clearance midway between the supports. Let weight of conductor is 1.5 kg per meter. Of the towers can be considered to be at water level. This is the question for you.